Hey guys! Plot twist. Unlike what we said in the last video, today's not about interfaces.
Yeah, there's something important we want to tackle first, something that'll help you handle data more efficiently.
Today, we're diving into how to sort datasets in a smart way.
Yeah. First, we'll talk about sorting algorithms in general. What makes some sorting methods stable or unstable, and how we can measure their speed and memory usage.
A sorting algorithm is like a ninja move, a step-by-step way to arrange items, like numbers or bananas in order, usually from smallest to biggest.
Imagine a bunch of bananas with expiration dates flying in all messy. The algorithm helps us line them up neatly, starting with the one that goes bad first.
Some sorting algorithms keep the original order of equal items intact. This is called a stable sort.
Say we first sort the bananas by expiration date. Now we want to sort them by their color value. Here's the key. If the banana with best before date, June 25th, originally came before the one with the best before date June 27th, it will stay in that order even though both are now just labeled yellow. That's what a stable sort does, it respects the earlier order of equal items.
But if you're using an unstable sort, that order might break.
Meaning the bananas with best before June 25th and June 27th could suddenly swap places, which could mess up your sorting moves. You should be aware of that.
Now, let's talk about how fast a sorting algorithm works. This is called runtime complexity.
How fast the sorting is totally depends on how much of a banana mess you start with. And what the best, average, or worst case for a sorting algorithm is, depends on how the specific sort algorithm works.
Let's start with the best case. For our example, the bubble sort. Imagine your bananas are already sorted by their best before date. 23rd, 24th, 25th, 26th, and 27th. The SortoSceneBot 3000 just scans them once and says,
"All good."
No swaps. No stress.
Now in the average case, the bananas are a little jumbled. Not a total disaster but not perfect either. The SortoSceneBot 3000 needs to do some comparing. A few swaps here and there. A little work, but manageable.
And then there's the worst case in our example. The bananas are completely reversed, they start with 27th and go on with 26th, 25th, 24th, 23rd. Now the SortoSceneBot 3000 has to compare and swap everything. This takes the most time and the most effort.
If you want to find out if your sorting algorithm is efficient, you will always use these three cases to test the runtime complexity.
Big O is how we describe how many steps it takes to finish a task, depending on how many bananas, or data, we have.
More bananas usually mean more steps for our sortbot. But how fast the steps grow? That's where Big O helps. In the following example, we will show you the most important types of Big O notation. The examples do not refer specifically to sorting algorithms, but to algorithms in general.
O of 1, constant time. No matter if there's one banana or 1,000. The algorithm checks one banana, and boom, done.
O of n, linear time. The algorithm checks each banana, one by one. More bananas mean more steps.
O of log n, logarithmic time. The algorithm cuts the pile in half again and again, like a banana slicing master.
O of n log n, this one's a bit more work. The algorithm splits bananas into groups, sorts each one, and puts them back together.
O of n to the power of 2, the slowest algorithm of all. The algorithm compares every banana with every other banana. So many flips.
So remember, the more bananas you have, the more steps the algorithm needs.
Big O notation helps us choose the right sorting strategy, so we sort smart, not hard. Besides speed, sort algorithms need memory space. Some sorts copy bananas around, others swap in place. Here are 3 examples for you.
Our first example is quicksort. It works in place. This means we sort the bananas in one box. Since quicksort works recursively, only a minimal amount of extra memory is needed for the recursion.
A quicksort needs a pivot. We use our last banana. Bananas that are less than or equal to 26 go to the left, and those that are greater than 26 are swapped to the right. We now sort the left group. Our pivot is June 25th. None of the other expiration dates is greater than 25th of June. The 24th stays on the left side and the 23rd switches its position to the left side. Our new pivot is June 23rd. We swap the bananas, June 24th comes after June 23rd, so the 24th goes to the right. The left group is sorted.
Back to the right group. As pivot we choose the banana with expiration date June 30th. The first banana we compare has an earlier expiration date. It stays in place. July 3rd comes after June 30th. So July 3rd will go to the left side. The other bananas on the left side of the pivot stay in place because their expiration date is later. The banana with expiration date June 27th stays in place. The next pivot is July 4th. Because July 3rd is earlier, no swap is needed. The banana on the right side changes its position to the left, because July 1st is earlier than July 4th. The last pivot is July 1st. The banana to the left has a later expiration date. That's why it swaps to the right side of the pivot. The whole box is sorted.
One box, in-place swaps. The quicksort works in place. Its memory use is O of 1. Only a little extra memory is used for the recursion. Its runtime complexity in the worst case is O of n to the power of 2, and in the average case O of n log n. However, it depends on how well you choose your pivot.
The next algorithm is one that has a memory use of O of 1. The insertion sort.
It sorts by inserting directly in the array. Means it swaps in place.
It takes each element, like holding it in your hand, compares it with the elements to its left, shifts larger ones to the right, and then inserts the element into the correct position.
It's like sorting playing cards in your hand. You pick up the next card and place it where it belongs among the already sorted ones. Alright, so we're now building up the sorted part on the left. The very first element is basically our starting point, our sorted list. Now, what we do is always compare the element just to the right of that list with the elements already inside the sorted list.
We compare the banana that expires on June 24th with the one that expires on June 27th. Since June 24th is earlier, we move it to the left. Boom, our sorted list just got bigger. Next up is the banana with the expiration date July 4th. Since it lasts longer than the one that expires on June 27th, we just leave it on the right side.
Then we look at the next banana to the right. Now, all the bananas in the sorted list last longer than this one, so they each shift one step to the right. That way, the new banana can slide into the very first spot. Since July 3rd comes after June 27th but before July 4th, we insert the banana in between.
So, I think you get the idea. We just keep repeating this until all the bananas are nicely sorted.
And here's the cool part, since all the bananas are swapped around directly inside the box, or in programming terms, inside the array, we only need constant extra memory, so the space complexity is O of 1. The insertion sort sorts by inserting directly in the array. No significant extra storage is needed beyond a few variables. Its memory use is O of 1. Constant space. Its runtime complexity is O of n to the power of 2 in the worst and average case. Next we use a merge sort. Imagine the array we want to sort as a box full of bananas, where each banana has an expiration date. The bananas and their expiration dates represent the numbers in our array.
Okay, and do we just shuffle the bananas inside the box?
Not exactly. We'll need one extra box for merging. The extra box we use is an extra array. First, we keep splitting the box into halves, then halves again.
Until every banana sits alone in its own little slot.
Right. Splitting is free, no extra space yet. Now we'll need one extra box for merging.
We take two bananas, compare them, and place them in order inside the extra box.
Good. That's the key, every merge fills part of the extra box with sorted bananas.
So each time I merge, the extra box grows to match the group size?
Exactly. The bigger the group, the more space the extra box must hold.
Wow, the whole extra box is full now.
Yes. In the last step, you need as much space as all bananas together. That's this merge sort's memory complexity, O of n.
Because the extra box must be big enough for all bananas, even if only temporarily.
Yes, in this example we used a classical top-down merge sort with recursion. Its motto is, divide and conquer. The top-down merge sort with recursion works by splitting the list into halves, sorting each half, and then merging them into a new array. Needs extra space for the merged lists. The memory use is O of n, the extra memory is proportional to the size of the input. Its time complexity is O of n log n, in both the average and worst cases. We found out that this was a top-down merge sort. If we have a top-down merge sort, does that mean there is also a bottom-up merge sort?
Of course. And it is iterative. Using a bottom-up merge sort, we start with the smallest pieces and build upward. Let's use the TwinSort to demonstrate a bottom-up sort. We found this interesting sorting algorithm on GitHub and will link it in the bio. The TwinSort begins directly with a so-called twinswap. The bananas are grouped into pairs and sorted in ascending order by expiration date. Next comes phase 2, called the tail sort. The algorithm begins merging the blocks. During merging, it always moves the right half into an extra box. This extra box represents the additional memory that is required. The first banana from the extra box, with an expiration date of June 23rd, is compared to the bananas in the original box. Its date is earlier, so it goes into the first position in the box.
The next banana from the extra box is compared. It has a later expiration date, so the other banana takes the second position. Next comparison, again, the banana from the original box ripens earlier, so it takes the third position. Finally, the banana from the extra box is placed in the fourth position. The next two pairs are merged in exactly the same way. Now comes the final merge. The 4 bananas on the right are moved into the extra box and compared with the bananas in the original box.
After this step, all our bananas are sorted.
This merge sort requires less memory than the classical merge sort.
The extra box holds at most half the amount. With 8 bananas, that means no more than 4. Its runtime complexity is O of n log n, in the average and worst case.
The iterative bottom-up merge. The blocks are merged from bottom to top.
You can see the block sizes grow as 1, 2, 4, 8.
There is no recursion, only flat iteration.
The top-down merge.
Here, the list is first split all the way down to single elements. Then it is merged from the very bottom back up to the top. This involves more steps and requires recursion. Great! We've now sorted all of our banana boxes. Sometimes faster, sometimes slower, but all the bananas are now in the correct order and we know more about sorting algorithms than before.
In our examples, we started with small arrays. But of course, the same techniques work just as well with larger ones. Sorting is extremely useful, especially when you're looking for a specific item. This applies both in real life and when searching for a particular element in a sorted array.
Here's a recent example. The sorticine bot 3000 placed a partially eaten banana into a box of 16 bananas, shortly before it was supposed to be shipped. According to the bot, the banana had an expiration date of July 3rd. In such situations, we want to find the banana quickly and efficiently. Instead of checking each banana one by one, we use binary search. This technique works on pre-sorted arrays, or in our case, pre-sorted banana sets.
Here's how it works step by step. We divide the bananas in half and compare the banana in the middle with our wanted one. The banana in the middle has an expiration date of June 30th. Since the bananas are sorted by date, we know that all 8 bananas on the left are earlier than our target date, so we don't need to check them.
Now we focus on the right half. We check the banana in the middle. It has a date of July 4th, which is after July 3rd. So we can ignore the right side of this half. We split the remaining set again. We find a banana with July 2nd, which is before our target. So we go to the right.
At the next step, we arrive at the banana with the expiration date July 3rd, our target.
By having the search space at every step, binary search lets us find the banana quickly and efficiently, even in larger sets. After 4 comparisons, we have found our target banana. If we had gone through the bananas one by one, we would have needed up to 16 comparisons in the worst case. Means a complexity of O of n. The maximum number of comparisons needed in binary search can be calculated with log base 2 of n. So in this case, log base 2 of 16 is 4. For an array with 100 elements, log base 2 of 100 is 7. And for one with 1000 elements, the result is 10. The runtime complexity in the worst case is O of log n. Alright guys, by now you should have a pretty good idea of what really matters when it comes to sorting algorithms and how to figure out which one works best for your needs.
And we've already seen how we can use binary search to quickly find stuff in our sorted lists. In our next video, we'll show you how to actually implement these algorithms in TwinCAT. Plus, we'll compare a bunch of them to see which ones perform the best.
So don't forget to hit that subscribe button, so you won't miss the next part on sorting algorithms.
Until then, have an awesome time, and drop a comment telling us which sorting algorithm is your personal favorite. Bye.
See ya.